Have you ever really thought about what it takes to build the future? I'm not talking about the next iPhone. I mean the actual, foundational technology for a whole new era of computing. Well, today, we're going to peek inside the quantum lab and meet the architects who are building that future, literally one atom at a time.
First things first, we have to wrap our heads around the scale we're dealing with. Forget about circuit boards you can hold in your hand. We're talking about a world so small that the normal rules of physics just don't apply. This is construction on an atomic level.
So how in the world do you get from an idea to a working quantum device? Well, here's our roadmap for today. We're going to start with the person doing the building, the quantum architect. Then we'll look at their strange materials and their incredible tools. We'll even step inside their workshop, see how they test their creations, and finally, we'll talk about why all of this really matters.
Right, so to build at this scale, you can't just be a physicist or an engineer or a material scientist. You have to be a new kind of creator, what we're calling a quantum architect. Someone who literally designs and builds structures at the very edge of what is physically possible.
And just look at the skill set for this job. It's an absolutely wild combination of disciplines. You need to be an expert in quantum materials, a master of manufacturing on a nanoscale. You need to work in ultra-sterile clean rooms, and then test your devices at temperatures colder than deep space. It's this unique mashup that has only just recently become possible. Okay, so let's talk about the building supplies. You obviously can't build a quantum computer with regular old copper wires and silicon chips. No, you need special bricks and mortar that actually behave in these strange quantum ways. One of the key materials is something called a topological insulator. And this stuff is just weird. Imagine you have a block of material that's a perfect insulator on the inside. No electricity can pass through. But the surface? The surface is a frictionless superhighway where electrons can flow with basically zero resistance. That's the kind of bizarre property these architects get to play with. And the other critical piece of the puzzle is the Josephson junction. This thing acts like a quantum bridge. You take two superconducting materials, you put a tiny barrier between them. We're talking something as thin as a single nanowire. And this little junction is what allows all the quantum magic to happen between them. It is the fundamental building block for so many quantum circuits.
So you've got your architect, and you've got your exotic materials, but how do you actually build with them? For that, you need a toolkit that can operate on a scale 1,000 times smaller than the width of a human hair.
And this right here is the fundamental challenge, isn't it? You can't just look through a regular microscope and use some tiny tweezers. I mean, when your building blocks are smaller than the very light you would need to see them, you have to invent entirely new ways of both seeing and drawing. And here they are, the tools of the trade. You got things like thin film deposition, which is kind of like spraying a surface with a perfect coating that's only a few atoms thick. Then there's reactive ion etching, which uses charged gases to precisely carve out patterns. And to see what you've done, you use scanning electron microscopes, which use beams of electrons instead of light to create an image of your tiny structure. You know, to really get the precision here, let's just compare two ways of drawing a circuit. Photolithography, that's kind of like using a stencil and a can of spray paint. It's good for bigger, simpler patterns. But electron beam lithography, that's like using a pen with a tip that's just a single atom wide. It draws the circuit directly onto the material. It's absolutely essential for the kind of detail you need for these quantum devices. Now, all of this incredible work happens in one of the most controlled environments you can possibly imagine, the clean room. This is a place where a single speck of dust isn't just an annoyance, it's a complete disaster. So let's walk through how it's actually done. It's this incredibly meticulous four-stage dance. First, you design the circuit pattern itself. Second, you lay down these whisper-thin films of your exotic materials. Third, you etch that pattern onto the layers with insane precision. And finally, and this is maybe the most crucial step, characterization. You use those powerful microscopes to check everything, to verify that every single connection is absolutely perfect. There is just zero room for error here. Okay, so the device is built. It's a microscopic marvel of engineering. But how do you know if the quantum magic is actually happening inside? Well, you can't just plug it into a wall socket. You have to take it somewhere very cold. And this is where cryogenic measurements come in. The best way to think about it is this. At room temperature, all the atoms in a device are just vibrating and jiggling around chaotically. It's noisy. And that thermal noise completely drowns out the super delicate quantum signals you're trying to see. To observe something like superconductivity, you have to cool the device down until that atomic world becomes almost perfectly still.
And when we say cold, we mean cold. We're talking about temperatures just fractions of a degree above absolute zero. That's negative 273 degrees Celsius. That's the theoretical point where all atomic motion just stops. It's only in this crazy, extreme environment that these devices finally reveal their true quantum nature. So, we've seen the architect, the materials, the tools, the clean room, the extreme testing. Let's zoom all the way back out and ask the big question. What is this all for? Why does this microscopic work have such massive macroscopic implications?
Well, the ultimate goal here is to merge these two amazing worlds, the practical world of building tiny things, nanofabrication, with the totally mind-bending principles of quantum physics. By creating these devices, researchers are building the foundation for technologies that sound like science fiction, quantum computers that could design new medicines in days, unhackable communication networks, and sensors so sensitive they could map the thoughts in a human brain. And that really leaves us with one final, powerful question to think about. For all of human history, we've built our world by shaping materials we can see and touch. But what happens when we finally master the ability to engineer reality at its most fundamental level? What new frontiers will be unlocked when we can truly design and build our world one single atom at a time?